Hey, welcome to this video, Rational Functions Part 1. Rational functions will start defining as a very similar setup to rational numbers. Why? Because rational numbers, as shown here on the top of the screen, is nothing else but a ratio of two integers, a over b, and the restrictions, of course, is that the denominator b cannot be equal to 0. So rational functions will be defined in very similar fashion. You divide this time expressions, polynomials, in numerators and denominators. The lowest degree of a polynomial is 0, then you have a constant value. So what you see here on the screen, 1 over x represents a rational functions. This is also known as a reciprocal function. So the numerator consists of number 1, which is a polynomial with degree 0, and the denominator represents an expression x. This is a term from a polynomial, which is actually a monomial with degree 1. So we do really have a ratio of two polynomial functions. And as you see, this blue line on both sides has red arrows pointing downwards. So this will be useful later in this discussion to determine whether this is a decreasing or increasing function. Okay, so the features of this graph are listed here. As x is approaching to positive or negative infinity, the values of function f of x are approaching to 0, which means that as x is increasing, as we read from left to right, as you continue increasing along x values, you'll see that the graph will be getting closer and closer to x-axis. If x will be decreasing, so the graph will be consistently approaching to x-axis as well. So the line here, x is equal to 0, or y is equal to 0, represents a horizontal asymptote, okay, which is shown right here. So this is the horizontal asymptote. Now, as x is approaching to 0 on both sides, then the graph is approaching either to positive infinity or to negative infinity, which defines the vertical asymptote. So the equation for that is x is equal to 0. So there's one vertical asymptote, one horizontal asymptote. When working with rational functions, also we'll be defining whether this is increasing or decreasing function. We'll be looking for positive or negative intervals. In other words, where the graph is below x-axis or above x-axis. We'll be looking for x-intercepts, y-intercepts, and at the end, when we have a graph structured, we will be able to define the range of the function based on what we see from the graph. So, the x-intercepts. So this is the definition right here. You're looking for points of intersection with x-axis. Since our ratio is 1 divided by x, so there's no way that you will get 0 from that division. Therefore, no x-intercept. Y-intercept is found when x is equal to 0. Now, our domain strictly says no zeros. Therefore, you cannot substitute x is equal to 0 into the formula, so no y-intercepts as well. The range of this function. So by looking at the graph, what you see here is that y coordinates would work for almost any real number except for 0. So the range will consist of real numbers. So y is element of R. such that y is not equal to 0. Okay, so this is basically the overview of the first most simple, straightforward rational function. And now we will do the example that involves a little bit more complex ratio. Alrighty, so this is the example right here. So first we'll define the domain. Domain is always a key for any rational function. So domain, usually you'll find the domain by setting the denominator equal to 0. So this is why let 2x minus 1 be equal to 0. You solve that equation and you get x is equal to 1 over 2. 1 over 2 would make the denominator equal to 0. Therefore, the domain is the set of all real values such that x is not equal to 1 over 2. Remember, x is not equal to 1 over 2, which means that there's a possibility of vertical asymptote at x is equal to 1 over 2. And we can confirm that simply by trying to simplify the expression. Since you cannot further simplify it, so you cannot make it simpler, 4x plus 2 divided by 2x minus 1, therefore this is the confirmation that the vertical asymptote is found when x is equal to 1 over 2. Now, this example also has another interesting feature. The degree on top is represented by linear binomial, which is 1, and the degree on bottom also is equal to 1, which means when you divide the numerator by the denominator, you should get a constant value and possibly a remainder. So in short, we will always say that when 2 degrees of the top and the bottom are the same, then the horizontal asymptote is always the ratio of the leading coefficients. So 4 divided by 2 is equal to 2. So this should give us the equation of horizontal asymptote. And this is the reason why, as I mentioned, when you do the division, so over here you see the division, when we divided the top expression by the bottom expression, and as a result you'll see that this is equal to constant value 2 plus 4 over 2x minus 1. This is the remainder. Now, as x is approaching to positive or negative infinity, so you're thinking, if I were to use a very, very large value for x or very, very, very small negative number for x, this whole ratio, 4 divided by 2x minus 1, will be very, very close to 0. So therefore, the value of the function for very, very large values of x would be approaching to 2. So now you have much better sense of why the horizontal asymptote is equal to 2. The next features of the graph is x and y intercept. So, of course, you want to find this by letting y value equal to 0. So this is why you say let 4x plus 2 is equal to 0. And this is the reason why. When you divide two quantities and the value of that ratio is 0, only because the top number must be 0. So when finding x-intercept, always use the numerator. So solve it for x, since x is equal to negative 1 over 2. So the x-intercept is defined as negative half comma 0. Remember, two coordinates, x and y. For y-intercept, however, you're looking for a value of y when x is equal to 0. So x can be equal to 0 according to our domain. And when solving this ratio, you get 2 over negative 1, which will give you exactly this point. Okay, so we almost have everything what we need to know about this function. Now we will attempt to graph. Okay, so horizontal asymptote is at 2. Vertical asymptote at 1 over 2. The key points also the X-intercept, Y-intercept. So we need to figure it out, what is the possible graph of this function. So what you see here, the two blue curves would represent pretty accurately, not very accurately, but good enough to show you that the graph consists of 2 parts here. And since we have only one X-intercept, one Y-intercept, there's no way that the graph could behave otherwise. Horizontal asymptote, y is equal to 2, is the line that defines the end behavior of this graph. The vertical asymptote splits the graph in 2 parts, so there's discontinuity at 1 over 2. The range of this function now consists of all real numbers except for 2, because horizontal asymptote is not intersected. So we can go and insert the values, the statement for the range right here, all real numbers such that y is not equal to 2. Positive and negative intervals. So this is, in other words, when the graph is above x-axis or below x-axis. So from negative 1 over 2 onwards to the left, so x is less than negative 1 over 2, or x is greater than 1 over 2. So this is this part of the graph, and the one above x-axis. For these 2 intervals, f of x is greater than 0. So the negative intervals will be defined only between negative 1 over 2 and positive 1 over 2. This is where the graph falls below x-axis. So x is defined in between negative 1 over 2, positive 1 over 2, and this implies that f of x is negative. Okay, increasing or decreasing intervals. Please note how this function behaves as you reading it from left to right and you continue sliding down. So this is a very intuitive approach. This is not a calculus course here. So this is why we say that by observation, as you read it from left to right, you decrease the values of y, which means the function is always decreasing, always. Okay. Since I'm using my magic marker, my ink is disappearing from the screen, but it is always decreasing. So what I have to do, quickly go and find a highlighter and highlight this, decreasing only. Okay, so this is the end of this video, part 1 on rational functions. I hope that you have enjoyed watching it as much as I was enjoying preparing it for you. So before the end of this video, please go and click like and post questions or comments right below the video. So I hope to see you next time. Thank you very much. Bye for now.